Alright, so today's video is the start of section 3.3, which is applications of exponential growth. Right, and first we're going to look at uninhibited growth, and then we're going to look at limited growth. Recall the exponential function is the only function for which its derivative is a constant times itself. This is actually very significant. Right? This is a very important and unique characteristic of its derivative, and that's what we'll be using in these applications. Alright, so what I mean by exponential is the exponential function in its most basic form. So the basic form would be this, right? Some function f of x. So again, something like f of x equals 10e to the 2x, something along those lines, where it's just a constant times the exponential raised to some simple number times the variable, right? So those are going to be the ones we're going to look at in the uninhibited exponential function. So when we say exponential function in math and science, this is the one we're talking about. Alright, so again, this simple function with a constant times the exponential raised to another constant times x. And that constant in the exponent, that k value, is a real number value, and that actually plays a significant role. Right? In some of our applications, we'll either be given it or have to find it. For exponential growth, that k is positive. Alright, and it has to do with the growth constant. If you remember from algebra, if you've taken an algebra class, or sometimes science classes, they talk about it as well. Alright, that k is, again, the growth constant. And we'll talk about that in a second in more detail. C is also a constant. Right, it's a real number value. And so when we take the derivative of this, the derivative is always the same. Alright, the derivative of a simple exponential growth function is always the original function times that k value. Alright, that k value. And this is just rewriting it. I'm going to take the k and multiply it by the c, and there's my derivative. Right, another way that the derivative can be written is it's the k constant times the original function, or the k constant times the function value y. Alright, and that's just another way to sort of write the same thing. Alright, if this is the derivative that we are finding, if this is the rate of change function we are observing, alright, so this is unique. If this is my derivative, where it's a constant times my function value, the only function that was possible was a exponential growth function, or decay. We'll get to decay in the next section. Alright, so again, that means it's either an exponentially growing or decaying, right, because the population is growing at a rate proportional to its size, right? The size would be the function value. K would be the rate at which it's growing. The only function that does this, consistent, this type of derivative, is the exponential function base e, which is why it's the common base, because a lot of things grow this way, grow at a percentage of its size. Right, that k is very important. It's called the relative percent growth, or again, decay rate, and we'll get to that in the next section. Right, to understand what that is, I'm going to do a couple of simple examples. I'm going to do an example of exponential growth and an example of exponential decay. Alright, so suppose we know that a population in a certain region is increasing by 13% per year. That would be the k value. 13% per year would be the rate at which it's growing. It's growing by a rate proportional to its size. The size would be 13% of whatever the population is. Alright, so suppose the population is 10,000. Alright? After a year, the population should grow by 13%. And so again, the first thing is we find out the 13%. So you take your 10,000, multiply it by your percent as a decimal, and that means 1,300. That's how many more people, right? And so that means we start with the original 10,000, and then we're going to add 1,300. And so the population after a year is 11,300 people, right? And that's what we mean by a rate proportional to its size. The next year, it would grow by 13% of the 11,300. All right, so 2 years later, it would grow by the new value. All right, again, it's a little bigger, it'll grow by a little more, but the consistent thing is it's growing at the same rate. All right, the size is getting bigger. All right, an example of decay. All right, a substance is decaying at a rate of 2% per day. Again, that would be the k value. It's losing 2% of its mass per day. All right, and so suppose we start off with, and this is how radioactive decay works. If you, again, remember from algebra or chemistry or biology or physics, radioactive decay works this way. So this would be some substance that decays by 2% per day. All right, so on day 1, we want to know, so 2 days, so we're going to do 2 days. So day 1, and then day 2. You can read that, day 2. All right, we want to know how much is left after the second day. All right, so in the first day, we started off with 100 grams. We're going to lose 2% of them in day 1. All right, so it's 100 grams minus 2% of that. Well, 2%, again, would be 100 times 2, or we're going to lose 2 grams. So at the end of day 1, we have 98 milligrams, which means at the beginning of day 2, that's how much substance we have left. And so to figure out how much is gone after day 2, well, you start with 98, right, because we already lost 2 grams. And now we're going to lose 2% of that 98. All right, so 98 minus 2% of 98, which is 1.96. Subtract the 98, or subtract the 1.96 from the 98, which means at the end of that day, we only have 96.04 milligrams left. And then on day 3, the same thing would happen. So day 3, you would lose 2% of the 96.04. All right, so you're losing it. Again, that's what it means by exponential decay. All right, or exponential growth works the same way. You're just adding instead of subtracting. All right, so these are examples of growth and decay. So the first one's an example of exponential growth. Right, I'm increasing, so it's growth. And the second one's an example of exponential decay. They work the same way. It's the percent at which you're gaining if you're growth, and it's the percent at which you're losing if you're decay. And it accumulates, right? After a year, I've got a little more, so I'll gain a little more. Or in the decay case, after a day, I lost some, so the second day I lose, but not quite as much, right? The second day, I'm only losing 1.96. The first day, I lost 2. And the next day would be even fewer grams lost, and so on as it continues, until the fraction's so small, we basically would consider it 0. Alright, so we have the following theorem. Suppose we know we can observe, right? We can do an experiment and observe that a quantity is growing at a rate proportional to its size. Alright, so we can observe that we lose or gain a certain percentage over the same time period. Alright, we can observe that. A lot of experiments, they do that. They observe that materials lose a percent so often, all right, in a reaction. And so if this is happening, we're again reading it with function notation, the K represents the percent at which I'm gaining or losing, all right, and so that would be the relative percent growth or the constant rate. And so if that's the case, if we can observe that it's increasing or decreasing at a percentage of its a proportion to its size, it has to satisfy this exponential formula, where C is a constant and K are constant. They're important constants. That C out front is actually my initial value, where my population started. So in the previous examples, when I had the population of the town, the 10,000 people would have been my starting point. Or in the second case, the 100 grams would have been my C. That would have been my starting point. All right, and so again, that's the initial value at time 0 where we're starting. And then the K is very important. All right, some applications will be given K. Some applications will have to solve for K. All right, this is what we call the growth or decay constant. It's the relative percent growth over a time period. It's the rate at which a quantity is growing or decaying over, and the time has to be consistent. So it has to be over the same time period they're losing the same percentage or gaining the same percentage, right? Every year they're gaining 13%. Every year, so it's the yearly. Or every day they're losing 2%. All right, so it's consistent. All right, so a simple sort of generic example. Suppose that we've made an observation, all right, and we want to find the function f of x that satisfies this information that we've observed. We've noticed that a quantity, which started out with 4 units, so that's the amount at time 0 when we started our observation, and then we noticed that it was growing by 50% per unit of time. Right, again, time would be days, months, hours, weeks, or whatever. Again, this is generic. So it's growing by 50% every hour if you wanted, right, to come out. And so what that means, it satisfies this. This is its derivative. This is its differential equation. It's growing by 50%, that's the percent written as a decimal, of its function value. Y would represent the function value. This is the C, all right? At time 0, when we were making our observation, we started with 4 units. Since that's the case, it has to satisfy that equation, a constant e raised to a constant times time. All right, and we know what C is, right? C is 4, that's my initial amount. K is our 50%, how fast we're growing. And so my function that satisfies this equation is 4e to the 0.5 times time. All right, and there's my exponential growth equation. So these are the type of the applications we're going to be looking at in this section. All right, so just kind of in general now, just kind of putting it all together. All right, so given a quantity, so Q just represents a quantity, so I just use Q as a generic. Q could represent anything. It could represent amount of material, it could represent a population. All right, so again, Q is just some type of quantity that's growing exponentially. So if it's growing exponentially, that growth constant's positive. The percent is positive. The initial amount, which again, a lot of times in math and science, we use this term Q naught. All right, Q naught means, Q naught is what we start with, all right? The initial amount, Q naught. And so this is the uninhibited growth equation, which you do need to know that, all right? Again, that's one of those things you just need to know. And this really should be something you've seen somewhere before, hopefully somewhere before. All right, what's unique about this is its derivative, right? Its derivative is always, right, the exponential function's derivative is itself, so the original expression, Q naught e raised to the k times t, times the derivative of the exponent, which is just k, all right? And that's always what the derivative is. It's the original function times its growth, and that should make sense. K is the percent at which we're growing, so we're going to multiply by k, right? Because k is a decimal, because that's how we multiply percents, is by decimals. And so another way to write this is our derivative, if exponential growth is our derivative, it's the amount of material I have at quantity t times the growth constant. That's always what this derivative is, right? That's the function at times t, the value at time t, times the percent at which it's growing, all right? And that's how fast it's growing at that time, right? And it would be in quantity. Units would be in quantity per time period. All right, so it would be milligrams per hour or people per year, all right, those types of units. All right, doubling time is very useful, right? If you, again, most of the time we'll either be looking for it or some applications will give it to us, all right, where we're looking for doubling time. And so sometimes we want to find it. So the first example is going to be looking for how we find it. And it's the same process every time. So either you can remember the process or you can remember the simple equation that we're going to find. And if you've ever taken math or science recently, this should look familiar to you when we get to the bottom of this. All right, doubling time means, again, it's a time that's easy to observe. I can observe when a population doubles, right? My population doubles every 4 hours, all right? Or my quantity declines, or I'm doing double time, not decline. My population doubles every 5 years, or something along those lines. All right, so I'm going to let capital T represent my doubling time, which means when I plug capital T into my quantity, I should have twice what I started with, all right? So I'm going to solve for that capital T, and so I'm going to plug this information in. So when I plug in my doubling time, my capital T, all right, I should have twice what I started with, all right? So I'm going to set my equation equal to 2 times my initial value, Q naught e raised to the k times my doubling time. Capital T represents my doubling time. And now I'm going to solve for t. First step is always isolate the e term, so divide by my initial amount. And what's nice about this is always going to happen. So it doesn't matter what my initial amount is. These two things will always reduce. And so on this side, I'm going to be left with 2. And on the other side, I'm going to be left with the e raised to the k times my doubling time. All right, remember, the next step is I got rid of e. Well, I get rid of e by taking the natural log of both sides. And so I get the natural log on this side equals our growth constant times our doubling time. And then to solve for the doubling time, we divide by our growth constant. And so doubling time is always the natural log of 2 divided by our growth constant. Coincidentally, if I go back to this step here, so I'm going to erase this here, if I know the doubling time, so if the problem tells me the doubling time, I can actually solve for k given my doubling time. So at this step, if I wanted to solve for k instead, so if I want to solve for k, well, I divide by my doubling time, and so k would equal the natural log of 2 divided by my doubling time. All right, and again, if you've taken a math class recently or a science class, those two equations should look familiar to you. And you can either memorize those if you want to and use them, or you could always solve like I did here. All right, so again, it's up to you if you just want to memorize that if I'm looking for a double time, it's the natural log of 2 over my growth constant, or if I'm given a doubling time, it's the natural log of 2 divided by that doubling time. We'll solve for my k. All right, and again, it's up to you if you want to memorize that or not. All right, now in general, all right, solving for k if we're just given any time, all right, so this would be if it's not necessarily a double time. So they give you some other, it could be just, in 5 years it grows by 10,000 or something like that. All right, what you're going to do, all right, so again, they give you a time and a quantity, and so we're going to just use this and solve for k. All right, so we start with, again, we'd know some quantity in the future. We know our initial amount, e raised to the k times some time, right? Time would be time they give me in the application. And so solve for k. First thing we do is divide out our initial amount. And so on this side we would have a fraction and we would leave it exact. Don't round. You could simplify it, but leave it exact. All right, so I would have whatever quantity at time t I'm given divided by my initial amount now equals my e raised to the k times t. And now I take the natural log of that ratio, that fraction, natural log of this side. And so here I'm left with the natural log of my quantity at times t divided by my initial amount equals k times time. And then divide by my time to find my k. Oops, divide by my time to find my k. Alright, so k would equal my quantity at times t divided by my initial amount all over the time that it took me to grow to that amount. Alright, and that would be, I'd be able to find k under any circumstance. Again, you could do the same thing for time. Alright, if I'm looking for a specific time, it would work the same way. You would just interchange the t and k. In this step here, instead of dividing by t, you would divide by k. You'd get exactly the same thing. So if I go back to this step, and I wanted to solve for t instead, well, I'd solve for t by dividing by my growth constant. And so I'd get my time equals that divided by k, and we can do that. And a lot of times we will be asked to do that. The biggest thing here is it's the natural log of this fraction where you don't reduce it, you leave it exact, no rounding until the end. And that whole thing divided by k. So the last thing you do is divide by k. Alright, so again, you can either memorize that or use it to solve. Alright, so we're going to stop there. On the next video, we're going to look at applications of this. So again, we'll pick this up here where we'll apply it. Alright, so that'll be the next video.